All right, so we're talking about the final exam review for Physics 206. And the first question is one here that I don't have a great picture for because I drew it on my own paper, but we have three positive charges organized in the picture. And then we're going to put a negative charge at the origin and talk about what happens to the force on the negative charge. So this is our negative charge here. I labeled that charge D, and then I just labeled the other charges A, B, and C. So I started at the top and labeled this red charge A. I called this one charge B and this charge C. So you're just using Coulomb's law or equation, which is KQ1, Q2 over R squared, and you're going to do that for each of the pairs of charges. So we're going to figure out how A would affect charge D, how B would affect D, how C would affect D. Now, in the diagram, it shows that all the charges are the same distance away, so they're all 0.5, so that's going to be the same number here for R, and then you square it. K is a constant, that's going to be the same, and then charge 1, I'm going to say is this -3. And then charge 2 is just whatever these charges are, so the 3 negative, or 3 positive, +3, +6, and +2. For all of these, they're nanocoulombs, so you're going to have to convert it into times 10 to the -9. So that's important that you do that. Essentially, I just looked at the interaction. So if A is positive and B is negative, it's going to attract. So that's going to be an upward force for A on D. And when I plugged into that equation there, I got the value of 3.24 times 10 to the -7 newtons. So that's the force pulling up. I worked in the Y direction. So again, if you have a positive charge down here, it's going to try to pull D down. So force of C on D. Again, just plugging into this equation with the values converted properly, I got 2.16 times 10 to the -7. That's going down. So in that tug of war, the upward is bigger, and it's bigger by this amount. So kind of just subtracted those two numbers and got this value for the net force going up. So this is the Y component. For the X direction, there's only one, so there's just this pull going to the right with this positive 6 nanocoulomb charge. So when I plugged in the same equation with the values specific for that interaction between B and D, I got 6.48 times 10 to the -7. So I have 6.48 times 10 to the -7 going to the right. I have 1.08 going up, and we want to know what's the net force. So we want to figure out what is this net force acting on our object. So to do that, we use the Pythagorean theorem. So it's the square root of these values squared. And I got 7.57 times 10 to the -7. So that is my answer to part A for the magnitude. For the direction aspect, it wants to say where is it going. So I didn't show this work here, but I'll do it right now. So I did the inverse tan for theta is equal to the y over the x, so it would be the 1.08 over 6.48. You could put times 10 to the -7 in both of them, but if you do that, they just cancel anyway, so you can just focus on the numbers out front. So inverse tan of 1.08 divided by 6.48, and that's what got me 9.46 degrees. And I had to just look at where is this angle measured from, so it's going right, so that's the positive x, and it's going up, so that's above, so that's why it's above the positive. Part B in this question asks, how would your answer change if it was a positive charge of 3 nanocoulombs instead of a negative charge? So if it was positive, all the forces would be reversed in nature. So if it was a positive charge, B on D would push it to the right. Force of C on D would push it up. And then the bigger force would be force of A on push it down. So again, you would get the same values and they would just add differently. So the way that I have it, it's going to go as the net force would be kind of the difference in these two, which is just a little bit down. So it's going to go like that. So it'd be the same angle. It'd still be 9.46, but it's going below the negative x instead of above the positive x, which we had now. So that's the answer here. Okay. So that's the first question on the review. For the second one, it's a capacitor problem. So it tells you information about the capacitor it says the area of the capacitor is 0.3 meters squared. It tells you the charge collecting on the capacitor is 9 times 10 to the negative 10th coulombs. And the separation between them is 5 centimeters, which turns out to be 0.05 meters. So in part A, it wants to know what's the potential difference between the plates. So this is the relationship or capacitance equation is Q over delta V. We're looking for V, so if I solve that, it's Q over C. So we know Q, I don't know C, so I have to do that from a different capacitor equation based on the physical properties, which is that one. So epsilon naught A over D is the equation that I use. Epsilon naught is just a constant, 0.3 is the area, and then 0.05 is the separation. So when I do that math in my calculator, I get a very small number, which is 5.31 times 10 to the negative 11th farads for the capacitance, and then I just plug that in this formula up here. So 9 times 10 to the negative 11, or 9 times 10 to the negative 10th is the charge divided by 5.31 times 10 to the negative 4, or negative 11, excuse me, writing's bad. That'll get me 16.95 volts. So that is the voltage across those plates. From there, it's just kind of using the other equations that relate voltage to electric field. So the voltage is equal to E times the electric field strength times the separation between the plates. So if we solve for E, it's V over D. So 16.95 divided by 0.05 is 339. And then based in the picture has the positive charges on the bottom and the negative on the top. So the electric field would be directed going from positive to negative. So this is where the electric field would go. So that those green arrows that I drew in, that's the direction of electric field. So that's why I said it's going up. And I drew it in this picture. Part D said if a negative charge is placed inside the capacitor, which direction would it move and why? So electric field lines show a force acting on a positive charge. Since this is a negative charge, it goes the exact opposite way. So the motion of the electron would go down because you can think about it in terms of electric field lines, or you can think about, okay, we have a negative and we have a positive plate, and we have a negative electron in the middle. So the negative plate's going to repel the negative, and the positive plate's going to attract the negative. So it's definitely going to move down. So it moves down. All right. So that was the second question about capacitors. Third question, asking about you have 2-point charges, and you want to figure out the electric potential at the midpoint between those charges. So first you need to know the electric potential. So I drew the picture. So it said we have a negative 25 times 10 to the negative 6 coulomb charge, so it's a microcoulomb. And I just called that A. And then B was the other charge, and that was 45 times 10 to the negative 6. And they're separated by 0.5 meters. And we're going to calculate at the midpoint. So if you take 0.5 and divide it by a half, the distance between each of the charges and the halfway point, the midpoint, is 0.25. So that's what we're going to use for R. All right. The potential difference equation is KQ over R. And you just do it for each one. So you need to find the net, you just add them. So we need to find the voltage or potential difference at A, potential difference due to B, created by that point charge. And then you just add them together. So again, positives and negatives are important. I showed the work here, it's a little sloppy, but it's 9 times 10 to the 9th times the negative 25 times 10 to the negative 6, and then 0.25. If you do that value, I got negative 900,000 for that one. And then repeating it for 9 times 10 to the 9th, this time it's positive 45 times 10 to the negative 6 and a 0.25. I got 1,620,000 for that one, and that one's positive. So if I add those together, the positive and the negative, I end up with 720,000 volts. So that's quite a bit of voltage. Okay, so that's part A. So this is all part A. For part B, it wants to know, determine the electric field between the charges and describe the direction of the electric field. So you need to figure out like the electric field created at a point. And again, we're measuring it at the midpoint. So measured it at the midpoint, the electric field created by a point charge is KQ over R squared. So it's almost the same equation, it's just got an R squared term here. So we're gonna figure it out for A, we're figuring it out for B, we're gonna figure out the directions. So this would be QB, okay, or A, or B squared. And you're gonna, again, sum them together, but this is a vector sum. So because there's directional aspects. So let's just draw in the directions first. So for A, it's a negative charge, so it's a negative charge. So the field is going to be going towards it. And then for B, it's a positive charge, so it repels away from it. So those two are both going to the left, and they're going to add together. So we're going to take these two numbers and just add them to get the net electric field at the midpoint. So what we're going to do is the plugging in, and I did that over here. So 9 times 10 to the 9th, positive 9th, and 9 times 10 to the 9th, times 25 times 10 to the negative 6 divided by 0.25 squared. That got me 3,600,000. And then when I did the same thing for just the 45 times 10 to the negative 6th, I got 6,480,000. So when I add those together, I get 10,080,000 newtons per coulomb. And again, it's directed to the left. So it's just, you don't have to worry about the negative here because the negative describes the nature of the electric field. Because it's created by a negative charge. So you just have to worry about the directions. They're agreeing, they're pointing the same way, so it's just addition to get that. Part C says if we put a positive test charge at the midpoint, so if we put a positive here, describe how it will move. Again, it's the same idea as what we talked about in the previous question. Opposites attract, so this positive test charge is moved to the left. The positive and positive, they are alike, so they repel. Or it's a positive charge, so it follows the electric field line. So you can use either of those kind of rationales behind it, but it's definitely going to move to the left. Okay, so that's number 3. Number 4 is quite a long problem because it's both a series and a parallel circuit. I made up my own charts and filled them in, but I tried to show a little bit work below. I didn't do all the work for all the pieces because it gets quite repetitive. But it's the same type of using the formulas and ideas as like for like A, for B, for C, for D. It's just with different numbers. So in the series setup, you got all of these resistors A, B, C, and D hooked up to a battery. That's in series because there's one path. And then in a purely parallel circuit, it would be hooked up to multiple paths, each having its own way to get back in the parallel. And the battery is 20 volts. So this is what I got for my answers, just to talk you through what I did. So for a series circuit, you have to find the total current. So the total current, I'm sorry, not the total current, the total resistance. So the total resistance, to do that properly for a series circuit, you just add them. So it would be 2 plus 6 plus 8 plus 22. So you add those up, that's 30 and 8, so that's 38. So 38 ohms is the total resistance, so that's RT. For the total current, you can do that by the total voltage divided by the total resistance, just Ohm's law. So big bad Ohm's law, the voltage is 20, 38 is the resistance, you divide, and you get 0.526 amps. And then it's rationalizing or understanding that all the currents are the same in a series circuit because there's only one path. So because all the elements are lined up one right after the other, they all have the same amount of current. So I put in 0.56 for all of those values there. So I have the currents, I have the resistance, I just have to multiply them to get the voltage. So I showed the work for A, but you do very similar work for B, C, and D. So 0.56 is the current that goes through resistor A, and the resistance is actually 2 ohms. So 0.56 times 2 gets you 1.052. So I did that for that answer. You would continue to repeat this process for each of these rows, and you should get these values for the voltage. To check, you can add up all these voltage. When I added them up, I got 19.988. I didn't go all the digits out, and that's why I didn't get exactly 20. The more digits you would go, the closer you would get, but that's close enough to me that I would say, yeah, that's complete. Then the last column is the power equation. So power is current times voltage. So to find the individual powers, it would be the individual current and the individual voltage. So you have the voltage, you have the current, so you're just multiplying these columns to get to the last column. So 1.052 times 0.526 gets you 0.533, and it's watts. So that's this work here. Again, B, C, and D have the same format. You're multiplying the two numbers here to get this column. So these are the solutions that you should get. If you want to check it, you add up all the powers to get the total power, and then you could use the total current and the total voltage. And again, they're really close. 10.513 and 10.52 are essentially the same thing. All right, so that's the series setup. The next one that I'm going to work through is the current, or I'm sorry, is the parallel one. So for parallel, again, I drew the picture. I can draw it again. So in parallel, every element it's on its own path, and it completes its own loop. So you got to do a little bit of math differently, but it's a lot of the same ideas with Ohm's law and the power equation. So the voltage across the battery is 20. The resistors are the same, 2, 6, 8, and 22. You don't just add them. You have to do the inverses, add the inverses, then take the inverse of that answer, and you should get 1.195 ohms for the total resistance of that parallel circuit. Remember, in parallel circuits, you're opening up more paths for the current to travel. So you're keeping the voltage the same and the current's increasing. So in Ohm's law, for that to work, the total resistance has to be less. So that's what happens here. So this resistance is smaller than any individual piece. That makes it up, just to make that a 6, more like a 6, that's fine. From there, I just found the total current because I'm going to check it later. So I did 20 divided by that resistance value. I got 16.736. The rule for voltages in parallel is that they're all the same. So again, each loop is adding and gaining and dropping 20 volts. So they're all 20 volts here. So I filled in this column all the same. And then again, you're looking for I out of Ohm's law. So V equals IR. If you're looking for I, it would be I equals V divided by R. So if you just take 20 and divide it by each of these individual resistors, you'll get the individual currents. So again, I showed the first one here for the current in A. So 20 divided by 2 gets you 10. You could do 20 divided by 6, 20 divided by 8, and 20 divided by 22, and you'll get these. If I add up all those currents, I got 16.74. That's essentially what I got there. So again, I'm checking my work along the way, and it seems all right. So I'm done with the first 3 rows, and now I'm just into the power equation, which is PHY. So I just have to do these two multiplied together. So 20 times 10 is 200. I showed that work down here. Again, similar work, just different numbers. So 20 times 3.3, 20 times 2.5, 20 times 0.91. Again, this will get you these values. You add them up, and you get the total power. I did it with the total current and total voltage, and I got essentially the same number. So again, I feel like that checks out, and I did the right thing. All right, so problem 4, a lot of like little individual steps and using Ohm's law and the power equation over and over, but not overly challenging, hopefully, for you. The next one is dealing with induction and current and flux and magnetic field. So it reads a flat square coil has 20 turns. So 20 turns, that's the N value. That's like how many coils make up the loop. It's rotating in a magnetic field. Each length is 15 centimeters. So 15 centimeters, 15 centimeters is 0.15 meters. And then it's a square. So if it's 15 here or 0.15 here, it's 0.15 there. So you gotta, when you multiply those out, 0.15 times 0.15, gets you 0.0225 meters squared. So that's the area that this rectangular or square loop of wire is. It has a magnetic field strength of 0.05. So we have B, we have A, we have N. And originally it's set up so that the field lines are basically not penetrating at all. They're just going to the right. And this is like the loop is flat and in the plane of the page. So there's no flux going through the loop. So no magnetic field lines actually go through parallel to the same surfaces. So initially there's no flux. Later on, after 2 seconds, this has rotated so that it is basically the maximum amount of lines going through. So it's like, if you imagine, it is perpendicular, the magnetic field is perpendicular to it. So this is the equation for a flux. It's just N, which is the number of coils, times B times A. So B is the magnetic field strength, A is the area of an individual coil, and since there's 20 of them, we multiply them together. Cosine this angle, cosine is 0 because the normal to the square loop is pointing in the same direction, so that's like 0, point the same way. So you get 0.0025 Webers because that's the unit for flux. To figure out the EMF, the induced EMF in this change, so going from the flat where no lines go through to where all the lines go through, you take the change in flux divided by the change in time. That's the or the voltage. So we got this answer. We divide it by 2 and we get the voltage. So 0.01125 volts is what we got for that one. Okay. So then it says, okay, if we connected this EMF to a resistor that had 10 ohms, how much current would be induced at that moment? So the current would be, this is just basically Ohm's law for our situation. EMF equals IR, so 0.01125 equals I times 10. So you just divide that value by 10 and you get that number. The last part is the kind of trying to determine the direction. So this is where the loop, I think, set up. So this is like the initial setup where it's like flat. So in the beginning, there's nothing. As it rotates, so in the picture, it says it's rotating in this manner. So we're like twisting. This is coming out of the page, and this would be going kind of into the page. You imagine that rotation. So it's gaining more lines going in. So there's more flux going to the right. So the induced magnetic field has to oppose that. So we have to make the current go so that the magnetic field lines that it creates is going against that. So in order to do that, we have to grab this loop of wire so that our fingers are kind of pointing back that way. So when we grab it, if we do that, our thumb points in the direction of the current. So, so when I do that, I kind of grab that loop of wire, and the current, my thumb, would point in that general direction. So I describe that as clockwise because it's going around in the clockwise direction. So it's going like this. So again, as it's rotating, my thumb is pointing up here with my right hand roll. My fingers would go through the middle, or if I grab the top part, my fingers would go to the right. So my thumb would go to the right, so my fingers have to go into the thing to make it go the other way. So that's a little confusing, but that's the work for that one. Number 6 is a mirror, and this is a different type mirror problem. So it says a dentist uses a spherical mirror to produce an upright image of a patient's tooth, which is magnified by a factor of 4.5. So the magnification is positive, and it's 4.5. Positive means it's upright. It's upright, it's a virtual image. You're putting the object the tooth 1.8 centimeters from the mirror. Right. So it has to be a concave mirror because concave mirrors can enlarge things. Convex mirrors cannot. They can only make smaller, virtual upright, so those match up, but they always make reduced images. So it is not convex, it has to be concave because they can make enlarged things. So for a concave mirror, we're going to solve for it has to solve for the focal length first. I solve for the image distance first because I think it's easier to use this magnification equation because you have 2 out of the 3. So I know the magnification, I know the object distance, I'm looking for the image distance. So I actually did C first and then B. I don't think you can do it the other way. So 4.5 equals negative di over 1.8. So you solve for di, you get a negative 8.1 centimeters. So that is the image distance, so where it ends up. So if it's negative, it's behind the mirror. And again, it makes sense that it's enlarged because this distance is bigger than the object distance. Then I can use the mirror equation, 1 over do plus 1 over di equals 1 over f, and solve for 1 over f. So I plugged in those values, and I got f as 2.3 centimeters. So that is my that's my focal length. So then I could sketch it. This isn't the best sketch, so I'll try to do another one. So if this is the rays of light, so this is the principal axis, let's make my mirror there. And then I have a dot to represent my focal length, which is supposed to be 2.3. My object is closer to the mirror than that, so it looks like that. So if I draw my rays, start with center line. So the first ray goes parallel, equal sign, and then X. I'm going to need to dot that back. The next one is the opposite of that, so it kind of lines up the focal point, the object, and the mirror. Center line would be better. So it kind of goes like that. I dot this one back. And then the last one always does the vertex. It hits the vertex, and then it bounces the same amount down, so that looks close to where it should go. And again, they're not going to intersect on the real, so they have to dot back and get you a virtual. So that is our image, this is our object, and that seems to check out with what was described in this one. Okay? So that one's a little challenging just in the way the problem's set up. I apologize for putting those two questions out of order. It should really go C and then B. Okay. So the last question here is another one that has a typo. So in the problem, it says light has a frequency of 530 nanometers. That's actually the wavelength. So that's a typo. I will mention that in class. The intensity of the light is 40 watts per meter squared. And it says it travels from flint glass. So this is the glass part down here. Starting in glass. And it's going to refract from the normal at an angle of 20.8 degrees. It tells you the index for the glass and then the ethanol, which is a fluid. And you're supposed to sketch the situation. So this would be my sketch. So this is the boundary, that horizontal line. My normal is the green dotted line. My angle of incidence is here. And with every boundary, part of the ray gets transmitted as long as it's at an angle of incidence less than the critical angle, which it is here. And then part of the ray is reflected. So this is my reflected ray down here. That reflected ray is the same as the incident ray. So whatever this angle is that it goes in at is the same angle that it comes out at. All right. So for A is just the sketch. B, it wants to know the angle of incidence. So I set up Snell's law. So N1 sine theta 1 equals N2 sine theta 2. That's the generic version of it. So we know theta 2, that's 20.8. Well, that's the refracted theta R. Sine is just sine, so that's going to fill in here. Ne is the ethanol that it's going into, so that's 1.36. That's the value for that. That is equal to 1.62 times the sine of the angle of incidence, which is what we're looking for. So I just solved this. When I did it, you might be able to see it a little better since I'm tracing it. It's 17.34. So I got sine of theta I equals 0.2911. You don't have to go out that many. If you got a slightly different number because of rounding, that's not a big deal. So, so that's part B, trying to figure out the angle of incidence that would cause it to refract at 20.8. That kind of makes sense, right? Because it's going into a less dense medium. So less dense means it speeds up. If it speeds up, it bends away. So this 20.8 is larger than the 17.3. So the way I sketched it made sense, and my math is supporting that answer. Then it asks you to calculate the velocity in each of the two mediums. So for both of these, I just use C equals N, I'm sorry, N equals, I used N equals C over V. And then I solve for V. So if I solve this for V, it's V equals C over N. So 3 times 10 to the 8th is the constant for the speed of light in a vacuum. We're going to divide it by whatever index of refraction we're in. So for the first one, it's 1.62. You can just do that part in your calculator and keep this as part of your answer. So that's why I kind of showed it here. So this is 3 times 10 to the 8th. So you get 1.852 times 10 to the 8th meters per second for glass. We said that it's going to speed up. So the value for ethanol is 3 divided by 1.36 times 10 to the 8th. So that's 2.206 times 10 to the 8th meters per second. So again, the velocity here is bigger than the velocity. Velocity in the second medium is bigger than the velocity in the first, so it bends away because it speeds up. It asks you to find the frequency. Frequency doesn't change. So frequency is a constant value. It doesn't matter what substance you're in. So if we started out and the wavelength in a vacuum is 530 times 10 to the negative 9, then we would just solve for F. So 3 times 10 to the 8th divided by the lambda, the wavelength, will get you F. So this got cut off, so let me write it out. So I got 5.66, I believe it's times 10 to the 24th. I'm just trying to give you that number. Yeah, so it's 5.66 times 10 to the 14th. All right, so that's your answer for the frequency in part D. For part E, it wants to know the energy of a photon of that frequency. So energy is just h times f. H is Planck's constant, which is 6.63 times 10 to the negative 34th. You multiply it by the frequency that we just got, and you get 3.75 times 10 to the negative 19th joules, or 3.75 electron volts. That's another unit for it. And then for the last question, you're looking for the electric field strength, or we're looking for E. So it's I equals 1/2 C naught E squared. So that's the formula you're using. You know C and E naught are constants. I is a value that's given to you, so you just have to plug in and get the value for E. And when I did that, I got 173. All right. So so that is the whole review, I believe. Sure that I got it all for you. Yep, that seems to check out. So hopefully that's a good preparation for what you need. Again, the final exam, there are going to be 7 questions total. You pick 5 for scoring. So you pick the 5 that you feel most comfortable with. They're 10 points apiece. All right. And I would say they're similar in nature to these. So if you can do well on these, you should be fine on the exam. So good luck, guys.